Okay. So let me start, and I want to thank Filippo and Andrea for inviting me to give this series of lectures. And I expected to give 5 lectures. So today it will be some introduction to large deviations and to the fluctuation theorem, and also Einstein relations. So the first lecture will be just introduction to large deviations. And okay, fluctuation theorem. And Einstein relation or fluctuation dissipation relation. Okay, so maybe uh, maybe some people already know. You see, do not hesitate to interrupt me. And also at the end of the first lecture, at the break, you could tell me whether it's too slow or too fast, and then I try to adapt to that. The second lecture will be on exact solutions. The third lecture will be about diffusive system, and about also the macroscopic fluctuation theory. Okay, the fourth lecture will be again the relation between microscopic and microscopic relation between micro and micro, and also on current fluctuations. And the fifth lecture, it will depend how fast I can go, but it will be again about current fluctuations because there are a number of things I would like to discuss. And maybe I'll throw also, if I have time, about ballistic systems. And then there are many aspects of it, including, for example, the problem of directed polymers or the problem, the KPZ equation or things like that. Okay, so let's go slowly. And the main kind of systems I have in mind are non-equilibrium systems. Also, if I write, okay, I could adapt, make larger writing. So the kind of system non-equilibrium, what I have in mind is a system which is in contact with, say, 2 heat baths or 2 reservoirs, uh, uh, 2 heat baths or 2 reservoirs of particles, and with different temperatures. And when the 2 temperatures are the same, the system is at equilibrium, and we know that the probability of finding any microscopic, the microscopic configuration of the system is given by, say, the Gibbs ensemble. So, okay, here it's a classical system, but anyway, it would also be true. So when you are at equilibrium, when T1 is equal to T2, then this is the starting point of equilibrium statistical physics. Now, when T1 is different from T2, the main problem is usually there is no expression for it. So the starting point of statistical physics, even if you are in a steady state, that is, you wait for very long, the system reaches a steady state, but you don't know what is this distribution. We will see some cases for which we can still write them, but usually you don't know. And this is a problem, and there is no surprise. It's not that nobody has discovered the formula, because what happens is that this steady state distribution, so the system you wait very long, then it might depend on the contact here and the contact there. So for example, if the contact is very weak on the right, then the system will resemble an equilibrium system at temperature T1. And beta is 1 over t. And if, okay, the reverse is true. So there is expression, but the reason is that if you try to get it, you need to take into account the contacts with the heat baths or the reservoirs. Okay. You can ask exactly the same system if instead of talking about system in contact between two heat baths, you have a system in contact with two reservoirs of particles here, and the system will reach a non-equilibrium steady state. Now, let me say something about large deviations. Now, large deviations, usually you're talking about a system where there is a number which is very large. So, for example, a large number of particles, a large number, a long time. So it could be this, or you could have a very small parameter. For example, you might look at a situation, and we will see that these situations occur where there is a very weak noise. You see, you have a system where the effect of the noise is very small. So, for example, you may have a gas, okay, no gravity or so, you have n particles in a volume V, and there is, okay, at equilibrium, there would be a constant density, and then this volume is very large, the number of particles is very large, and one question of large deviations would be to say, okay, what is the probability that if I cut my system into two parts, on this side, I will see a density ρ1, and here I will see a different density ρ2. Okay, so that I don't see the system as homogeneous, but for example, I would see a higher density in part of the system. So usually this will be something like the volume times a function of ρ1 and ρ2, okay, and maybe of the geometry. You see which part of the system I want to have density ρ1 and ρ2. So this is a large deviation function. This is a very unlikely situation, and you want to know what is the probability of this seeing this very unlikely situation. Now we will see maybe in a few minutes that in fact this quantity has a very clear and simple interpretation, and it is not just to care about events which essentially never occur. Okay, so for people who have never heard about large deviations, let me just say a few words about large deviations of some of large deviations of sums of IID variables, random variables. So this is the simplest case. And imagine that you have a sum okay, I equal 1 to t of xi, and the xi are just random. They are all distributed according to the same distribution. Okay, so okay, I'm sure that you know that if the system, the distribution here has decreases fast enough when you go to infinity, then you have for a large t, you have the law of large number, that is that x t over t goes to the average of x. That's the law of large numbers. And that the fluctuation of S, so the variance of S divided by t is equal to the variance of the variables, because they are not correlated. Okay, I am not going to repeat these things. If anybody wants, we can. Okay, these are supposed to be rather elementary. Now I can ask, what is the probability that the sum st over t it takes a value which is s, which is not with s different, this small s here is different from x average. So what is the probability that I observe a rare, that this sum takes a rare event, and this will be t times I of s. So this is the large deviation function of the sum of random variables. Now, usually, if I take a distribution of this xi more or less arbitrary, there is not a simple expression for that. But still, one can write a lot of things. So the first thing I want to do is to show an elementary case, or two elementary cases. To my knowledge, these are one of the very few cases where you can get explicit expressions. So the first example is what's called a Bernoulli distribution. Bernoulli. So xi is 1 with probability p, and 0 with probability 1 minus p. Okay? Then you can compute the average of st will be pt. You can compute the variance. And you see, probably everybody has done this calculation before. If you ask what is the probability that the sum st is equal to small s times t, then it's just you have this formula here, t, count the total number of ways that you can have zeros and 1 times p to the times 1 minus p to the t minus st. Okay, and then you use what's called Stirling formulas, which is rather elementary, and then you get, okay, just let you finish the calculation, you just replace st by this formula, and you get that I of s is equal to s log of s over p plus 1 minus s log of 1 minus s over 1 minus p. Okay, so this is one of very few cases for which you have an explicit expression. Now, what can I say about this expression? So let me just draw in this example what I of s look like. Okay, so this is the probability, yes. I of s is the probability that st equal t times, or st over t is equal to s exponential minus t I of s. So what does it look like? S, okay, s can only take values between 0 and 1. Okay, so it has a shape like that. Here, it vanishes when s equal p. Sorry, maybe okay, so it's positive. So okay, sometimes it depends whether I put a sign there. Okay, so it's something like that. For s equal p, it vanishes. Now, the function near the origin here, it looks like a parabola. Near p equal, for s close to p, it's like a parabola. And you see that this parabola If you put it in an exponential, this is just a Gaussian distribution. So if you, this neighborhood here tells you that essentially the distribution will become Gaussian if you don't look too far for deviations which are too large. Now, you take this formula, you can expand it, and you get that I of S equal S minus P squared over 2P1 minus P plus, okay, I continue 2P minus 1 S minus P cube over 6 1 minus P squared. And okay, so this is just, you expand this formula. Now, so what you see is that if, as long as S minus P is of order 1 over square root T, essentially, this will be 1 over T to the 3/2 multiplied by T. So this does not count. So you get the Gaussian, what's called the central limit theorem, that the distribution is Gaussian. But as soon as you take S minus P, even of order 1/3, say, and of course, or larger or equal to 1/3, this term will start to contribute, and many other terms will contribute. And so the central limit theorem is only that you have a Gaussian distribution is only valid if you are looking at deviations of order 1 over square root T for this S here. Otherwise, the formula is different. Okay. Now, there is another case that you can solve, but I am not going to spend much time on it. So this other case would be just that rho of x, so second example, rho of x would be exponential minus x for x positive and 0 for x equals 0. So you have a distribution. This is again a case for which you can calculate explicitly the distribution, and you find that I of S, okay, it's a calculation which takes, okay, I hope in fact, I am not sure I wrote it here. Yeah, okay, it's given by S minus 1 minus log S. Now, in general, you have not an explicit expression, but you can write it in a parametric form. And we will see in other cases, especially in the fourth lecture, that often the results, when you look at current fluctuations, appear as parametric form. So let me talk about the general case still in this situation, simple situation of sum of independent random variables. Of course, this is just in the introduction, because what is interesting is the case where the variables are correlated. So now let me suppose that ST is x1 plus xt, and all these variables are independent, distributed according to the same distribution, rho of x. And now I would like to know what is the I of S, the probability distribution that, as I said before, probability that ST over T equals S exponential minus I of S. Okay, something which is simple is to compute the generating function lambda of st. And lambda of st, because the variables are independent, is just lambda x1 times x2 times a. So it's lambda lambda of x1 to the power t, because they are all independent. So this, let me call exponential lambda x. So the average, this integral of rho of x dx, let me call it exponential mu of lambda. Now, in in general, I of S will be given by, in a parametric form, that is I of S. Okay, let me see where I have that in my notes. That, okay. Okay, let me first say something. Okay, so essentially exponential lambda S of t will be integral of small ds exponential minus I of S plus lambda S to everybody times t. So this is the probability of st, and this is the value of st. And so this is the probability of capital ST, and this is the value of ST. And you expect that this, okay, when t is very large, then this will be of the form mu of lambda, where mu of lambda is here, because we can compute that directly. And if you think that you can use a saddle point here, because t is very large, you use a saddle point, and this will tell you that mu of lambda will be equal to lambda s minus I of s, and the value of s, which is here, okay, so this, sorry, if you use a saddle point method, you will get that mu of lambda is the maximum over s of this expression. So essentially, if you knew I of s, you would know mu of lambda, just because you have this integral, and for large time, for large t, this is dominated by the thing, this is a saddle point or saddle point calculation. People are familiar with saddle points? Or? Yes, okay. Okay, so this is, you know I of s, you get mu of lambda. If you want to do the reverse, there is what's, okay, then if you want to do the reverse, the mu of lambda needs to have some properties that it's differentiable and so on. And I'm not going to discuss that in big detail, but you see, this is a kind of this is a Legendre transform. And in fact, under some math conditions that I don't want to discuss here, but which is called the Gardner-Ellis theorem, then you can invert this, and then you get that I of S is given by lambda mu prime of lambda minus mu of lambda, and S is equal to mu prime of lambda. So the thing to remember in this simple, say, general example is that if I give you the distribution of the variable x, then you have just a single integral to compute mu of lambda. Now, if you know mu of lambda, you want I of s, then you have this formula here, which, okay, so this is just, you invert this Legendre transform, and it appears in a parametric form. So if I want to draw I of s as a function of s, then you vary lambda. As lambda varies, s varies. As lambda varies, I of s varies. And so you can draw I of s as a function of s. So if people are interested, I encourage them to just take the two examples I mentioned before, and then just to compute the mu of lambda, that's difficult, and then to see that you recover the I of s using this formula. Okay, so this is for independent random variables. But of course, what is interesting is when variables are correlated. And free energies. You see, the first thing I want to say is that if you think of asking about large deviations of correlated random variables, it's a huge field. Essentially, many problems in physics, in statistical physics, can be formulated like in terms of computing properties of sums of correlated variables. Okay, so let me just give you an example, which is related to uh, uh, so you see many problems can be formulated that way. Now, the thing I am going to ask about is if you have sums of random variables which are correlated, now, as before, I could ask what is the probability that this sum of correlated variables decays like this, and what is this? Now, questions one can ask is I of S convex, which it is for IID, it is convex, but okay. What is the difference between correlated variables when a system at equilibrium or out of equilibrium? Difference between equilibrium and non-equilibrium. And we will see that there are major differences. Can one compute? Is it interesting? And so on. Okay, so one thing I want now to show you that this object I of S, which looks something like talking about rare events that probably never happen. In fact, it's very related to the free energy. And so it has some clear meaning. And so let me take again the example I had before, that I have a box and I have n particles, but these n particles in volume V. Okay, and so there is a density rho equals n over V, and I want to ask, okay, these particles, they collide and they interact and all the kind of things, and I would like to know what is the probability that all the particles are on the left in this volume V1, which is alpha V. Okay, so I want all of them. So this will be a very rare event. Now, what is the probability that all particles are in V1? Okay, so it's the sum over all the configurations of these interacting particles, of the Boltzmann weights, of the configurations where all particles are in V1. And it's divided by sum over all configurations where all particles are in V. Okay, because the probability, this is just, I count only configurations where particles are on this side. Now, this is the partition function of having n particles in V1 divided by the partition function of n particles in V. And this is an and Z of V and N, or N and V, I don't remember. Okay, it's just exponential minus the free energy of the system divided by the temperature. Here I just put the Boltzmann constant to be 1. So essentially, you see, if you know the free energy of the system, it's related to the large deviation function because the probability of this rare event is just exponential the difference of free energy between these two situations. Yes, so the probability of P is just exponential. Okay, so it's exponential minus f of v plus f of v over t divided by t minus f n minus f of v1 n over t. So this very rare situation is the same, telling what is the probability of this very rare situation is the same as telling the difference between free energy between these two situations. So this is just to mention that these rare events, okay, you see, that's a really physical quantity that we all know about. And now if you imagine that the system is extensive, f, which means that f of v and n, I want to write it as v times a function of v over n, that is v a function of rho, then this would really take the form of exponentials. I hope I made the minus v over t times alpha f of rho over alpha minus f of rho, where v1 equals alpha v. Okay, so essentially, when the system is very large, you have this very large parameter in front, the volume of the system, and this is the free energy as a function of density per unit volume, this small f. Okay, so this is just to tell you that the large deviations is very related to the free energy. Okay, now in some lectures to come, I am going to talk about the functional of the free energy. Yes. Okay, maybe before I want to say that, you see, you know that the free energy is a convex function. Now, I don't know, are people surprised if I say that free energy is convex, or I can, yes or no? Sorry? What does the word convex mean? The word convex, okay, a convex function is a function which is like that, it has its curvature. So you just count, which is the same as saying that the function, the second derivative is positive. Okay, so the free energy is convex, and knowing that f of rho is convex, you can show that this is convex also. This large deviation function is convex. And I want to say that in non-equilibrium systems, we can discuss similar things, and we will see, or I don't know whether I have time to go there, but sometimes this large deviation function is not convex. But anyway. Now, let me talk about a quantity that I am going to discuss a few times and discuss it now at equilibrium, is functional of the density. So I discuss it in one dimension, but you can do it in arbitrary dimension. So let me just imagine that I am at a temperature 1, so I don't want to care about the temperature. And also KB is 1, more or less all the time. And now I have a very large system. And the system is itself uh, consists of large subsystems. So imagine I have L equal K small l. And now I would like to know what is the probability that the density in the first box is rho 1 and the density in the last box is rho k. So that this means that in this box I have n1 particles, L times rho 1 and so on. And so the probability of rho 1 rho k will be essentially, okay, I, essentially exponential, okay, it will be, okay, so it will be essentially minus L, a functional of rho 1 and rho k. Okay, it will be a large deviation function now, which will depend on all these things. And now I want to know what is this functional. I want to write it. So if I have a very large system and I want to think of a large system, and I want to think also that this system has short range interactions. It's very important. Then what I want to show you is that this functional, okay, this functional will be given by 1 over k sum of f of rho I minus f of rho bar minus chemical potential mu of rho 1 minus rho bar. Okay, so let me try to show this formula. Okay, so I have k boxes, and I want to show this formula, and here there is a chemical potential. So I want to think of this system in equilibrium, and I want to see I want to show this formula, and after that we will talk about a functional. Okay. So what is the partition function of everything, of all possible configurations of the system, without specifying what are the rules there? Okay, it will be just the denominator. I will have z of n and v, or v of n, I don't remember, over volume and n, and then I have exponential mu n over t, but t is 1 at the moment, but if you want to put it. So this is all the possible configuration of the system, and here I have a weight, which is the chemical potential, because the chemical potential is you see, there to equilibrate the system with a reservoir of particles. And now in the numerator, I will have, okay, so here I want to write something. I want to look at all the boxes. And in the first box, okay, here it's L, because I am in one dimension. Z small l of n1 times product of Z of L minus nk. And this probability is given by that. In fact, it's not exactly given by that, because the particles which are inside the first box, they might interact with particles on the other, in the next box. But now I have supposed that these boxes are very large, and these interactions are just surface effects. So essentially, this is not equal, but it's very close to being equal, given by that. And what we have forgotten here, of course, is the effect of the chemical potential. So it's exponential mu times n1 plus nk. Yeah, this is with a chemical potential, the partition function with exactly n1 particle, and this is with n1, and okay, and each of these sum here is uh, is dominated by a certain value of um, a certain value of n. So in the numerator, you have exponential minus sum of f of rho I minus L, sum de this term, plus mu sum of rho I. And in the denominator, you have minus, so this is I equal 1 to k, I equal 1 to k, and in the denominator, it's L, and here you have L, c'est rho bar, or the density in the whole system, and here you have plus LF of rho bar. Okay, and if you look at this, you get you get this as this sum. So the, the probability of observing this is given by formula here, where you have only the free energies of the system plus the chemical potential. And for those who remember a little bit of thermodynamics, then I want just to write that just in terms. So what is what? So sorry, where is the typo? Oh, I see. Okay, so I do this maybe. No, no, yes, yes, no. You are right. Yes, yes. So I remove that. Yes, sorry. Okay, fine. So what is rho bar is the density. You see, if you have a system at equilibrium, this would be the total density at of equilibrium of this large system. So this means that when you do this sum here, when the system is very large, one range of n will dominate this sum. And the range of n which dominates this sum will be, so this n which dominates is equal to L times rho bar. Okay. Yes. So okay. You don't need to do that because here I have a system with a chemical potential, so it can exchange particles with reservoirs. But you could also discuss a different situation, that is, you fix the total number of particles, you have no exchange, and you would end up with the same formula, in fact. Yeah. By here, so sorry, okay, so this thing, and what else? Okay, when I say this thing, it's because, you see, if you look at this is as if all these boxes did not interact. But in fact, they do interact. And the interaction will produce something which is very small compared to the main result here. Okay, you can have prefactors. You could even have, you see, here I am talking about in one dimension, but if I was in dimension arbitrary dimension, I would have L to the D here, and the thing which would be neglected are surface effects. So it would be with order of L to the D minus 1. Because you see, if you do it in 2 dimension or in higher dimension, you are going to break your large system into sub-boxes. The interactions between boxes are surface effects, and this would do this contribution. But the main contribution is this. Is it okay? Okay, should I stop now? Okay. So you have this expression. Okay, I wanted to finish that before the break, but let me say this expression. You can also think about the functional. Now, one thing that you have to remember, okay, from statistical physics, is that the free energy as a function of V. Okay, so the derivative of the free energy with respect to the number of particles is just the chemical potential. Okay, so this means that here I am talking about the extensive part. That's really elementary thermodynamics also, and this means that the mu which is here is just f prime of rho. Okay, if people are not so familiar with that, we can discuss it, take a little more time during the questions or something. Okay, the thing I want to say is that you can think of a functional that is now, instead of saying I have k boxes, I take many boxes. So I imagine that L is very large, that the boxes themselves are very large, but the, they are much smaller than the whole system. Okay, so now I want, instead of having a sum of terms, I want to replace it by an integral. And at equilibrium, so then I can say that the probability now of observing a certain density profile, this is again at equilibrium. What I am discussing here is always at equilibrium, will be a functional exponential times L times functional of the density profile. And this functional would be just to replace this sum by an integral. So this functional of rho of x will be integral of f of rho of x minus f of rho bar minus, okay, so I replace mu by f prime of rho bar times rho of x minus rho bar dx. Okay, so this is a functional of the density profile for a system at equilibrium. Now, I want to, okay, one thing first is that here, you see, particles are interacting. You see, it's not that it's the density or the number of particles in a box is the sum of independent random variables because they are interacting. But one thing which is very characteristic of system at equilibrium with short range interaction is that this is a local functional. This is a local. This means that there is no thing between rho of x, rho of y. There is not a double integral. And we will see that out of equilibrium, large deviation function of the density becomes non-local. Okay, but this is just local. Okay, so now I want to discuss an aspect uh, very much studied in the case of large deviations is the case of Markov processes. And many of the systems we will discuss are Markov processes. So my so you can consider a discrete or a continuous time. Markov process, yes? Yes, but this is also interacting particles. You see what this formula tells you that, for example, you take the 3D Ising model. I don't know I have not an explicit expression of the free energy, but still this formula is true. This is, you don't need the thing to be non-interacting. The thing you need is that the interactions are short range, but they could be a distance of 10 lattice or whatever. Sorry? But yes, but saddle point doesn't mean that the system is not interacting. What is used is that the system is very large. And so the main thing is that when the system is very large, essentially you can consider that at leading the free energy of the whole system is essentially the sum of the free energy of each boxes, because you have only surface contribution. This is what you are using, but the particles can interact as much as you like inside. Short range, yes, yes, yes. Short range means, for example, you take Ising model where two neighboring sites interact. Okay, so for example, you have the, the energy of a configuration would be sum of potential per potential, but this V decreases fast enough with the distance. That's short range. Okay. Other question? How fast? Okay, how fast? I think if it decays fast enough, like exponential, if it decays exponentially, but presumably if it decays power law, that the power is fast enough. Probably it's not true when you have uh, Coulomb interactions or things like that. Yes, and there are okay, maybe you see there are exercises maybe I can give where you will see that this is not true when the interactions are long range. Okay, so there are no other questions. Yes, 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 yes. And you see, when people look at critical phenomena, usually they add some gradient terms to that. But here I am talking about a system, and I don't talk about really critical points. So you see, but even when okay, I don't want to enter the story of the critical points here. Okay, so let me come to Markov process. Okay, so Markov process is a simple case of interacting particles, but interesting. Many of the models I am going to discuss here are in fact from a microscopic point of view Markov processes, and it is just that you are interested in a sum x1 plus xt, but now the probability of xt plus 1 say, depends on xt. So you have to know what was the previous value and to tell what is, okay, so let me say rho. For example, you could say that xt plus 1 is 1/2 with probability xt and is 1 with probability 1 minus xt. So you start with xt equals 0, and then the first thing is 1, then the second one will be 1/2, and the third one will be either 1/2 or 1. Okay, this is an example. So the probability of one value depends only on what happened before. And you have, in fact, many systems that you can describe like that, because here I am talking about numbers, but this could be very high dimensional vectors and so on. So this is what's called a Markov process. And so the probability of time t of observing x is just integral of rho of x given y, probability of having y at time t. Okay, so this is a discrete time Markov process. Now, there is a continuous time version. In fact, the continuous time version is just a limiting case of the discrete time. Okay, so you say that x at time t plus dt is very short time, infinitesimal, is xt, or is y. So this would be with probability 1 minus integral of rho of x given y, sorry, probability given xt. So you know xt. This is the probability that it does not change. So this is, and it becomes y with probability rho of y given xt dt. And I have in mind that dt is very small compared to 1. Okay? So this would be a continuous time. And in fact, you see that this is just a particular case of this case, because the change from time t to time t plus dt is very small. So this is a special case. So this is a Markov process. And many of the models that we are going to discuss here are Markov processes. So one of them, in fact, will be what's called the symmetric exclusion process. Okay, SS, so it's a symmetric simple exclusion process. And okay, it's a one-dimensional system which consists of L sides, and then you have particles on this lattice, and during every time dt very small, each particle can jump with probability dt to the left or to the right. But so it's called symmetric because the rate at which you jump to the left or to the right is the same. Simple because you jump only to the nearest neighbor. And exclusion because you cannot jump to a site which is already occupied. So this is one example. And on top of it, you can uh, have particles entering the system from the left and on the right and exiting. So you see, this is an open system, and you have some rate at which particles enter on the left or leave on the right, on the left, and the same on the other side. And this is an example of the system which will be out of equilibrium. For example, if you take alpha equal 1, gamma equals 0, beta equal 1, delta equals 0. So you see particles can enter from the left. They cannot leave because gamma equals 0. They cannot leave on the left. And they leave on the right. And they cannot enter from the right. So there will be a flow of particles. The system can reach a steady state in this, for this system. Okay. So now a configuration of the system will be given by to 1 to L, where to I is 0 or 1, depending on whether the site is occupied or empty. And I am interested in the probability of seeing the system in a configuration C. So this configuration C is just, there are 2 to the L configurations. It's a, L is, if L is large, it's a huge number. And so this will be, what I am writing now is very general for Markov processes. There will be a matrix which tells me that, so this is the probability that at time t, the system was in configuration C prime and it jumped to configuration C because Markov process, the probability of being in C at time t plus dt depends only on where I was at the previous time step. And then there is plus 1 minus sum over C prime, m of C prime C dt times pt of C. So this is just a rate equation. Ever at the previous time step, ever I was in C prime and I jumped to C. Okay, this is m times dt is the probability of this jump, or I was in C and I did not jump to any other configuration. So this is the evolution. And so if I, so this becomes, when dt is very small, which is assumed in all these things, there is a master equation. Sum over C prime, which tells me how the probability of seeing the system in a configuration C evolves. That's called the master equation. And in situations where the Markov process is irreducible, irreducible means that somehow there is a way, a path, a possible way to go from any configuration to any other configuration. So here it's very easy to see that I see the case for an example like that, because I could start with everything empty and I start to fill the system by letting particles enter. So I can go from any configuration to any other configuration. And what happens is that if you are in this situation, so irreducible, implies that Pt of C go to stationary in the long time limit stationary distribution. But it's not an equilibrium, you see, because as I said, when alpha is 1 and beta is 1, for example, and the other parameter is 0, there will be a flow of particles. When you have a flow of particles through your system, it's not an equilibrium. Still, it's a steady state. Okay, here I don't take it time dependent. Now there is the whole field that I am not going to discuss here of what is called stochastic thermodynamics, where you make them time dependent. For example, if you want to to describe a system on which you change the landscape potential or something. For example, when you uh, put some force on the system and you've changed its volume, also you would have these things which are time dependent. But here I don't take them. Okay. Now, if I take this system, the matrix M consists of three parts: M1 plus M bulk plus M2. Okay, because to jump from one configuration to the other, describe what happens here. Okay, so there is a probability that I jump from one configuration to another due to the interaction on the left. M2 will be the same on the right, and M bulk would describe all the moves inside. And we will see that when the system is out of equilibrium, essentially each term tries to equilibrate the system at a different density or at a different temperature. Now, okay. Now, the, now I want to discuss something rather important is in terms of these Markov processes. Okay, let me keep this one. It's what's called tilted matrices. Now, if I take this example, one quantity I might be interested in is to count how many particles have gone through the system. So you see, to say what is the current through the system, and I want to know what is the average current, what is the fluctuation of this current, or what is the large deviation function of this current. So I observe the system during time t, and I might be interested in qt, say the number of particles entering the system during time t. Okay, and I want to think of this time to be very large. So large deviation would be to say what is the probability that qt over t takes a certain value I of q and exponential I of q. I want to know, for example, the large deviation function of this uh, this current. Now you see here at the moment t is large, but the system here has a size L. It has a size L here, but I don't need L to be large. It could be a very small system, and I want to know how the current through the system fluctuates and what is this large deviation. Now, to do that, I am going to introduce what's called tilted matrices. So instead of talking about this specific example, I want to consider a quantity which I write like this. Qt is sum over So let me take a discrete time just as an example, but okay, so discrete time Markov process. And I want to say, okay, tau equals 0 to t minus 1 of q of c tau plus 1 c tau. Okay, so I have a quantity which depends on which configuration I am in, which configuration I jump to, and I have a function here. Okay, so for example, here if I am interested in the number of particles which enter this system, okay, Q, sorry, this is tau, Q of C tau plus 1 C tau is each time a particle enters, so I am in a configuration says that this was empty, the new configuration is that particle enters, then this Q becomes 1. If, say, I am in a situation where I allow also particles to leave the system, this Q would be minus 1. And if there is an internal move, this Q would be to 0, because here I am counting what is entering the system. But you could decide that you want to count something else, and this is a quantity. Okay, so I'm interested in a quantity like this. So it's essentially general for Markov process. And now I want to write the evolution of the probability that the system is in configuration C at time t, and that I have observed Q of t. So now I am, yes? Yes, so I don't see. Okay, maybe I did not take the number of particles entering the system at time t, and this is a more general thing, but the number of particles entering the system during time t is a special case of this quantity. Up to time t, yes. So is it okay? See, okay, this is the integrated current. So you count during time t how long, how much. Okay, so let me just write what happens for this thing, and very much like I had this formula here, I have probability of being in configuration C at time t plus 1. Okay, I take a discrete time Markov process, and I observing Q at time t plus 1. It will be sum. At time t, I was in an arbitrary configuration. I jumped from Ct to Ct plus 1. And here I had the probability of being in Ct and observing Qt minus Q of Ct plus 1 and Ct. Okay, so how is it possible that I observe Q at time Qt plus 1 at time t plus 1? Okay, I was somewhere before. Okay, I have jumped from Ct to Ct plus 1, and when I did this jump, Qt increased by this amount. Okay, and this looks difficult. So this maybe this at time t, and this is at time t plus 1. And this look difficult thing because a priori, because okay, here for an example like that, I have 2 to the L configuration. So I have a finite number of configurations. So the probability Pt is just a vector, okay, with many components, but it's a finite vector. But now Qt can become very large. It is unbounded. So it could become So this acts, it's still a Markov process, but it's a Markov process in an infinite dimensional space. So it looks very difficult, but there is a very simple way to simplify the problem is to introduce generating functions. So let me call p tilde or p hat of ct pt. This would be just exponential lambda qt times the probability of ct and qt. And I sum over all possible qt. Now, I just can take this formula, multiply by exponential lambda qt on both sides, or lambda qt plus 1 at time t plus 1. And what I end up with is that p t plus 1, p hat of c times t plus 1 is sum over ct of m of ct plus 1 ct times exponential lambda qct plus 1 ct times p hat of ct. Okay, so you just multiply both sides by this exponential, and you just sum over qt, and you get this thing. And you see what I have gained doing that is that, as I said, ct takes 2 to the L possible value, qt takes an infinite number of possible values. So this in principle is something in an operator with infinitely many possible values. But this here, this matrix is a finite dimensional matrix. For the SEP, for example, is 2 to the L by 2 to the L, which is still a big thing, but this is a finite matrix, and now I have this recursion. And the consequence of that is that if I am interested in the long time behavior of this, yes, sorry. So there is a sum of, sorry. Uh, no. Okay, q t plus 1 minus qt is q of ct plus 1 and ct. Okay, so yes, okay. You can do whatever, okay. You can make it imaginary. You see, okay, maybe I am assuming that this number is bounded or something like that, but you don't need, in fact, to be imaginary. If you like, okay, whether you take it imaginary or real or whatever, doesn't matter. Okay, but the main point, okay, is so again, you had this evolution there. Now, okay, here I am talking about discrete time, but there is the same thing with continuous time. But what happens is now you have a matrix, which is a finite matrix, maybe 2 to the L by 2 to the L, as long as I look at finite systems. And what happens is that you know in advance what will happen for large T. What happens for large T? You have a vector, a matrix times a vector. So for large T, pt hat of C will grow like T exponential mu of lambda, where mu of lambda is well, in this case, exponential is the largest eigenvalue of the matrix of the following tilted matrix. And the matrix, you can read it here, is m lambda of C prime C, which is just m of C prime C exponential lambda q of C prime C. Okay, so you see, because after all, this is just a vector multiplied by a matrix. And if you multiply a matrix many times, then what comes out is what you get is the largest eigenvalue of this matrix. It's a finite uh, problem. So this is called the tilted matrix. Is it okay, or I can? So if I just try to summarize this story, the following. Sorry, I am slower than I expected. So if I am interested in exponential qt, which will be the sum over qt, maybe the sum over all configuration of pt of c qt exponential lambda qt, and this we say that, okay, let's sum over c, sum over qt, and we say that this, we called it p hat of c. Now, all the p hat of c will grow like the largest eigenvalue of this matrix. So this will grow like exponential mu of lambda times t, and mu of lambda is the largest eigenvalue of this tilted matrix. Okay. Yes. No, it's not. No, it's not known. Okay. It's not, no, Qt is a random variable. So, for example, when I had the exclusion process, Qt will depend on the realization of the Markov process. Sometimes the particle enters, sometimes it, so I have many events, and Qt will fluctuate. And so I am just looking at the generating function of Qt. I hope I am, yes, you have a question? What you could have a potential if you like also, but there is a steady state in the system. We will discuss the steady state in more details, but essentially, you see, you will see a density profile which is linear, which is, but okay. So let me consider a simple example, and you can, in order to think about this thing, let me consider the following simple example, which is a SEP with one side. Now, one side. Sometimes people call it a quantum dot, but anyway, there is very little quantum in it. So, but anyway, so this is just an example where you have one side, so it can be either occupied or empty. So the system has two states, either occupied or empty, and particles can enter with rate alpha, leave here with rate gamma. If it's occupied, they could leave on the right with rate beta and enter with rate delta. Okay, this is system. So what is, and now I'm talking about the continuous time. So I have two configurations. There is configurations A, which is occupied, and B, which is empty. And the probability of being occupied depends on time, also the probability of being empty. So what's the matrix M? The matrix M is minus alpha. Here I have, okay, let me see. It's minus, sorry, so the first thing will be occupied, so minus beta plus delta, and here I will have alpha plus, no, sorry, what do I do? Okay, minus beta minus gamma here. Here I have alpha plus delta. Okay, here I have beta plus gamma, and here I have minus alpha minus delta. Okay, so this is a matrix. I have two possible states. If I am in an occupied, I can leave the system at rate gamma on the left and beta on the right. This is this term. And if I leave the system, I enter the empty state with this rate. So this is a Markov matrix, the M of CC prime. What is the tilted matrix? The tilted matrix, if I am interested in the number of particles entering, so okay, so if I am interested in Qt here, what will be the tilted matrix? Then each time a new particle enters, I get an exponential lambda in the system. So this becomes exponential lambda, and each time a particle leaves the system, I get an exponential minus, sorry, no, yes. Okay, so I was in state one, I get an exponential minus lambda. So this is the tilted matrix. I recommend that you just try to think about this very simple example. And now you can try to get the largest eigenvalue of this matrix. Okay, it's a 2 by 2 matrix. You can do the computation by hand if you like, but there are a number of facts that I am going to mention about this problem. Okay, there are a number of very interesting facts because they are very general. So this is the tilted matrix and mu of lambda. So you know that exponential lambda qt will be given by exponential t mu of lambda, where mu of lambda is the largest eigenvalue of the matrix, eigenvalue of m lambda. Okay, so now you see before I had exponential mu of lambda, the largest eigenvalue, because I was in discrete time. Here I am in continuous time, so mu of lambda is the largest eigenvalue of this matrix. So why I don't have? Because I am interested in the number of particles which enter the system from the left. Okay, so to answer your question, I could do what you said. I could say, I am not interested in this Qt, but I am interested in the thing which is here. I want to compute how many particles leave the system here. Let me call Q tilt. It would be a different current a priori. Okay, so what would be the matrix? It would be minus beta minus gamma. Here I would have alpha plus delta exponential lambda, beta exponential lambda plus gamma, and minus alpha minus delta. So this would be a different tilted matrix. Now, you can imagine that if I am looking at very long time, the number of particles which enter will be the same as the number of particles. So I let you check that this matrix and this one have the same mu of lambda. And it's very easy to do because these two matrices have the same trace and they have the same determinant. Okay, one thing I want to mention, but I think I have to stop soon. Oh, okay, but so I am slower than I expected, but anyway, it doesn't matter. Okay, so this mu of lambda here is the same as this one here, but in fact, you see, if I had a set not with one side, but many sides, it would be still the same if I count the number of particles entering on the left or leaving on the right, because the particles cannot accumulate. Now, something you can notice about this matrix here is that it has an additional symmetry, which is very important. And this additional symmetry that if so there is this matrix M of lambda, and now I am interested in F with a different values of lambda, where lambda prime is equal to gamma delta over alpha beta exponential minus lambda. So let me just consider these two matrices. Just I have made this replacement. Now you can check easily that mu of lambda is mu of lambda prime. Just you replace in the matrix. And this is a special case of the fluctuation theorem, which is much more general. And okay, I was planning to explain what it is today, but I will postpone that later. Okay, so this relation, okay, you can do it by hand. So first, you have to convince yourself that this is the right tilted matrix. That what I said, that the largest eigenvalue of this matrix will tell you what happens in the very long time. That's just a fact about linear algebra. You just multiply a matrix many times, and you get the largest eigenvalue. It dominates everything. And the point is that there is a symmetry, and this symmetry has to do with time reversal symmetry also, but this is a particular case of the fluctuation theorem. Okay, so maybe I should stop here now if you like, but okay, I had in mind that I would be faster. So okay, yes, okay, yes, presumably. Okay, I don't know what will happen, but presumably I am slower than I expected. Maybe if I am too slow or too